right, so here it says determine if the function is continuous or discontinuous, and we're just going to use a C or a D. And if it is discontinuous, then we'll categorize it as either a removable discontinuity, which is a hole, a jump, or an infinite discontinuity. Okay, so sometimes it's helpful to take a look at the function and say, all right, what does this graph look like, and what's the domain of this function? So when I take a look at x squared plus 1, what is that as a graph? It's a quadratic, which looks like a parabola. And what's the domain of a parabola? All reals. So basically, there's no place that, if I were to sketch this graph, do I pick up my pencil at all? No. So in this case, my domain is all reals. So is there any place where this function is not going to be continuous? No. So it's continuous all the way around, right? So we don't have to identify any discontinuities. But when I look at B and C, they both have the same denominator, but they are different scenarios. So let's look at B. Whenever you have a function that has a variable in the denominator, you need to factor, especially if it's a quadratic or cubic. So I'm going to rewrite this as x over x plus 3, x minus 3. Oftentimes we'll look to see if there's a hole. In this case, do I have a hole? No. What do I have here? I have 2 vertical asymptotes. Okay, so in this case, we definitely have a function that is discontinuous. All right, and my discontinuities occur where? Where x is equal to plus or minus 3. So we have infinite discontinuities at x equals plus or minus 3. Right, because they're both vertical asymptotes. So then when I look at C, which is a little bit different, when I factor, you have x minus 3 in the numerator, and then x plus 3, x minus 3 in the denominator. So we have 2 different scenarios here. What's the first one? Definitely not continuous. Agree? Yeah. Discontinuous, D. Okay, and what are they? I do. We have a hole where? At x equals 3, and then what else? Yeah, I have a vertical asymptote, which is the infinite discontinuity. So basically we have a removable discontinuity where x is equal to 3, and then an infinite discontinuity at x equals negative 3. So those are our 2 scenarios. Okay, questions with rational functions?
Do we also put the coordinate that it's like x3 and
for the whole?
Y, yeah.
No, you don't have to. Not unless it specifically asks for the coordinate of the whole. In this case, it just says removable discontinuity because it didn't ask for it in the directions. Okay? Okay, so what we have here is a piecewise function. I'm skipping D and moving on to E. And in a piecewise function, what we need to take a look at is what is happening here. So for any value less than 0, we have a linear function. And anything greater than or equal to 0, we have a quadratic. So we need to see, is that going to be an open circle there, depending on what happens, or is it going to get filled in by the other function? So what we need to do is evaluate the limit as x approaches 0 from the left, which is going to be our linear function here, which means we plug in 0 and I get negative 1. And then we'll evaluate the limit as x approaches 0 from the right, which would be our quadratic, which means I get positive 1. So graphically, what's happening? If I'm approaching from the left, so this is from your perspective, I'm down here at negative 1, and that's going to be open or closed. Look at the inequality. Open or closed? Open. And then I have my quadratic as I'm coming from the right, and it's going to be a closed circle, but I'm up here at positive 1. What is this? Yeah, I have a jump discontinuity. They're not coming together at all. So this is definitely discontinuous. And you have a jump discontinuity at x equals 0. Okay, because that's our x value. Okay, before I move on to F, does anyone have any questions about E? Okay, so in F, again, we have a piecewise function, and it says that your function is made up of x squared minus 1 over x plus 1 only when x is not equal to negative 1. And clearly you can see when you plug in negative 1 to the denominator, we get a 0 in the bottom, right? Regardless of what happens in the top, it's still going to be undefined or indeterminate. But also visually, what do you see? Okay, I have a hole. So if I rewrite this right here, what I want to see is, we could have a graph that has a hole in it, and it could be approaching from both sides but still have a hole, right? What we want to know is, to determine if this is continuous, does that hole get filled in, or does it stay open and I have a point somewhere else? So we need to see what that limit is. So what we're going to do is evaluate the limit as x approaches -1, okay? And we're going to factor this, x plus 1, x minus 1, over x plus 1. And remember, this was one of the algebraic methods for us to evaluate limits using direct substitution, because what does this allow me to do? Yeah, I can cancel out the whole. So my x plus 1s are gone, and I'm left with the limit as x approaches -1 of x minus 1. So now I can use direct substitution, right? This is just a linear function. So what is the limit? It's at -2. Okay, so basically what this means is I can sketch my graph, but I know at the point -1, 2, it's an open circle because we have a hole. True? Okay, but then what does the next line say? When x is -1, what is the y value? So what does that mean graphically? What happens to that hole? Yeah, it gets filled in, it gets plugged. So is this function continuous, yes or no? Yes. Okay, you let me know if you change your mind. Okay. Does anyone have any questions determining if a function is continuous or discontinuous, removable, infinite, or jump discontinuities? What you have to do if you're determining if the function is continuous. It is all about the limit. That's the whole reason that we were talking about the limit forever. Okay? All right. So, notation. This is the biggest thing right here. Continuity on an interval. So, if you are asked to identify over what interval a function is continuous, you need to write your answers in interval notation. Interval notation. Okay, so please make sure you carefully read the directions. So I'm just going to go over this really quick because most of you know this already. If you are given an interval over which this function is continuous on an open interval, remember it does not include the endpoints. Here, your endpoints are included. Here, this is considered right continuous at A, which means A is included, or left continuous at B, where B is not included. So I'm just going to show you what the graph looks like quickly. So at the top, we have an open circle at A, open circle at B. So something like this. We'd have closed at A here for the second one, and open at B. So this is A, this is B. Here we have closed at A, open at B, and vice versa here. So open at A and close at B. Again, this just gives you an idea. So here the directions are: identify the interval over which each function is continuous, because we're going to talk about the x values or the points or whatever. But here we want to know the interval. So really, what we're looking at is a domain. Where is this function continuous versus not continuous? So here we're looking at the domain. All right. Let's see. This is just a square root function, right? No rational function, meaning there's no variable in the denominator. So tell me some characteristics about a square root. Remember, you are graphing this on paper, so you have to be able to pick and plot points. What can you not have? Is there any place where this is not going to be defined? Negative numbers. What about 0? Can you take the square root of 0? Yes. Okay. So what you're saying is that any value or what you have to have underneath the radical has to be greater than or equal to 0, meaning positive or equal to 0. True? Okay. So in order for us to identify the domain, you have x plus 5 is greater than or equal to 0. This is just a simplistic way to do it. Then you have x has to be greater than or equal to negative 5, which in interval notation means you have negative 5 to infinity. That is the interval over which this function is continuous. All right, let's take a look at a cubed root. Characteristic for cube root. Can you take the cube root of a negative number?
Yes.
Positive? 0? Is cube root ever undefined anywhere? Okay, so what's a domain? All reals. So if you think about it graphically, okay, the graph looks like this, right? So that should make sense. So in this case, your domain is either all reals, however you want to write it, or negative infinity to positive infinity. Typically, if it says the interval, you need to write it in interval notation. Okay, again, I said this to 7th period. Apparently, I don't know what my alphabet is, so this is a double D. Here, this should be E. Okay, let's take a look at C and E. You guys can go back in the notes and look at the true D here. So we have variables in the denominator. So tell me one thing. Regardless of the fact that it's under a radical, what can you not have in the denominator of a fraction if you had to graph? 0. Okay. So we know that whatever we find for the value of x, we cannot create a 0 on the bottom. This is the 4th root. It's an even root. So you guys told me you could take the cube root of a negative number. Can you take the even root of a negative number?
No.
So tell me about the radicand, which is the quadratic under the radical. How would I set this up to solve for my domain? You told me it cannot be equal to 0. Okay, so I can't use the equal to like we did in A. What else? Can't be negative. Greater than 0. That's the only thing I can do, right? Okay, so what we're looking for is what is going to create a 0 underneath this radical or a negative value. So we're saying, okay, anything that doesn't create that must be greater than 0. Meaning my x values will have to be greater than 0. So what we're looking for is what would create for x a positive solution. So we would have to factor this. So this is x minus 4, x plus 2 is greater than 0. Do you guys remember this from pre-calc? Okay, we've talked about this already. We have to throw these values on a number line and figure out which interval or intervals will give us positive numbers. So I'm going to put a number line right here. I've got negative 2 here. I've got 4 here. So we're looking at 3 intervals that we have to test. So if you forget the multiplicity thing, I'm just going to do this quickly when I'm testing the intervals. If I go over here and I pick 5 from this interval, 5 minus 4 is a positive. 5 plus 2 is a positive. That means this is a positive. Agree? Pick a value from here. The easiest one is plug it in. What does it give you? A negative. Right here, pick negative 3. What does it give you when you multiply? Positive. Okay. Remember the multiplicity thing that I told you about. Multiplicity of both of those factors is even or odd? It's odd. Guys, what is the degree here is a 1 and a 1. Is 1 an even or an odd number? Odd. Okay? That's why I'm reviewing this. Okay, so that you understand it. So that means because both factors have an odd multiplicity, I can start over here and say this is positive, negative, positive. It'll alternate each time. Okay, does everyone see? If you forget or you don't know, did you see I just plugged in the values? It's not a big deal. Okay, so now what we're looking for, any values greater than 0, meaning we're looking for positive scenarios. Where does that occur? From where to where and where to where? That's right. Is negative 2 included, yes or no? No, it is not, because it's not equal to, right? Union, negative 2 to infinity. So it's this one right here and this one right here. You guys remember that? Oh, 4. Woo, buddy. Thank you. Not only do I not know how to count, but I can't use the alphabet either. It's a good day all around. Okay. Thank you. If you go back and watch the video, this is done a little bit differently, and there is a missing piece, so you really do need to pay attention to this. Okay. So in E, we have a variable in the denominator, but we also have a natural log in the denominator. So overall, we know that the denominator can or cannot be equal to 0. Cannot. So that means, just listen, this whole piece, I need to figure out the value or values that would make it 0 and not include those in my domain. Do you see what I'm saying? Okay. In addition to that, can I take the natural log of 0? Think about the graph. Think about the domain of the natural log. We just did it the other day. What's at 0 for a natural log? What's there graphically? If I had to graph the natural log function, what does it look like? I'm seeing all these things. Well, it goes like this. Because remember, it is the inverse of e to the x. Right? Okay, what's at 0? Don't say. Who said it? A vertical asymptote. So, can the natural log be equal to 0?
No.
What about a negative number? No, it cannot. You are correct. You said it emphatically. No. Can we take the natural log of a negative number? Look at the graph. No. So, let's deal with this part first. You're just going to agree, right? No. Okay. This part, meaning what we take the natural log of, must be greater than 0. Agree or disagree? You guys just told me.
Agree.
Thank you. All right, so we're going to take, for the first part, 4 minus x squared and set it greater than 0. So we just did this in the previous problem. We'll have to do a number line test, meaning I need to factor this. This is 2 plus x, 2 minus x is greater than 0. So what type of values are we looking for when we test? Positive or negative? Exactly. So I'm just going to do this quickly with values. When I plug in negative 3, 2 minus 3 is negative. 2 minus a minus becomes plus. So is this positive or negative here? It's negative, because this is 2 minus 3, which is negative 1. 2 minus a negative becomes plus, so that's 5. So this is negative. Plug in 0, what do you get? Positive. Plug in 3, what do you get? Okay. You told me we wanted positive, so that means we're right here. So far, true? So any value between negative 2 and positive 2, not including those values, will give me a positive number to take the natural log of in the denominator, right? Okay, now we need to figure out what's going to make this whole thing not equal to 0. So we need to take the natural log of 4 minus x squared and set it equal to 0. And when we find these value or values, we can't include those in our domain. If they fall outside negative 2 and positive 2, then we're okay. But you have to test. How do I solve this thing without a calculator? Yeah, you exponentiate both sides. Nice. So when I take e to this, e to the 0, right? What is e to the natural log of 4 minus x squared? What happens here? Gone. And the 4 minus x squared drops down, right? What's e to the 0? 1. So now we have 4 minus x squared is equal to 1. Can we solve this? Yes. Okay. So we have negative x squared is equal to negative 3. X squared is equal to 3. So we're saying that x cannot be equal to, because this is what would create a 0 on the bottom, plus or minus the square root of 3. Okay, just to give you an idea, the square root of 3 is about 1.7. How do I know? Because I've done these notes before. Just saying. I don't have it memorized yet. Okay. Anyway, what I'm saying is those values fall in here. So when we identify the domain, we have to basically say negative 2 to negative square root of 3, not included, negative square root of 3 to the square root of 3, and then the square root of 3 to 2. Whoa.
Union.
Sure. Okay?